All right, in this screencast, we'll be going over the paper, Model-Based Reinforcement Learning via Meta-Policy Optimization. You may recognize there's Peter Abil, OpenAI in Berkeley, a Berkeley OpenAI paper, basically. Cool. So let's have a quick overview of the paper. So this paper gets around requiring really accurate learned models using meta-learning on data synthesized by an ensemble of learned models. So, okay, none of the models are right, but whichever one is right, it can adapt to that very quickly later. I think that's the basic idea. So the policy that it learns this way can perform well where the learned models agree, and since it uses meta-learning, it can adapt between the models and hopefully to the real world as well very quickly where there are model discrepancies. So here's like a quick overview of the algorithm. You repeatedly collect transitions from the environment and train your model, and then you do a step of meta policy optimization where on each of your different models you train an adaptation of your meta policy and then you update the meta policy to make the adaptation better. That's basic meta policy learning. So you created these adapted policies, and those are the ones that you actually run in the environment to collect additional data to train your models. Cool. So that's the algorithm. In more detail, here's their write-up. Cool. So let's talk about how this worked, why it's an important paper. So it works well. It has the asymptotic performance of model-free methods, so generally model-based methods are not performing as well. It also has excellent sample efficiency. Like model-based methods, I'm not sure if it's quite as good as model predictive control, but it has excellent sample efficiency compared to general model-free methods. Cool. So, and it also has excellent performance compared to other model-based methods. And even when the models are strongly biased, which is usually an issue with model-based methods, this can still perform very well. So it gets around that problem. Cool. So why is this an important paper? I'd say it's because of the excellent results, one, and it has a very clean method for dealing with model bias. There's been other methods which we'll look at. This has a really nice, clean, kind of intuitive approach to dealing with that. Cool. So now we'll move into the meat of it by looking at some related work first. And we're going to look at how to address the inaccuracies in learned models. So there's been a number of approaches. You can use very simple learned models, but this has limited applicability. Then there's using an ensemble of models, because we know none of them are right, but you can kind of get the errors going various different ways to see where you don't. That can show you where your models are not working well, right? Because the models disagree. There's various ways to get this ensemble. You can add random noise to a single model, or you can just train a bunch of separate models. And then once you have this ensemble, there's a few approaches. One approach is robust policy optimization. That's where you create a policy that performs well on all the models, right? So you're like, I don't know which model is right, but as long as the actions I take will work well on any of the models, then things are good, right? So the downside of this, so this works, it results in conservative policies, and it sounds like it can be complicated. I don't know the details of how to create a robust policy. And then there's this paper, which instead of making it work well on all the models, it does meta policy optimization so it can adapt well, right? And the result is that it actually ends up being robust where the models agree. And where the models disagree, that's where it ends up being adaptive. And just think for a moment, why would it be robust where the models agree? So, and pause the video for these, right? So I think, if the models agree, so in meta policy optimization, you want it to perform well after one step of adaptation, right? So a great way to have it perform well after one step of gradient descent is to have it perform well before. So I think that's all that it's doing, is if the models agree, then just make it work well in all the models. If the models disagree, well, then we can use our adaptation step to actually adapt, right? But if they all agree, we might as well make our meta policy perform well on all the models. So meta optimization, I think, should give basically the same result as direct optimization when the tasks are identical. Cool. So another approach is to learn adaptive models. So this is meta policy optimization again, that quickly adapt to new settings. And I would say this is online, right? So your humanoid is running and the terrain changes and it does a policy update and adapts right away. So here, everything's fine, it gets onto some new terrain, and then it just does a gradient update right there to adapt. And lastly, there's the old method of, okay, we can do model predictive control using our bad model, but at every step we replan because we know we're making mistakes, and so we want to kind of catch the mistakes and fix them as soon as possible. As soon as the time horizon becomes short enough that our model is working well enough. Cool. All right. So now let's look at how model-based methods and model-free methods have been combined. So there's a few approaches. One is backpropagating through the policy you learned. It's not a good idea. You get vanishing and exploding gradients. Another approach is to imagine data, like synthesize data with your learned model, and to train a policy on that. Now, there's a few approaches. You can either augment real-world data with an imperfect model. I'm guessing you stay close to the paths that were actually taken and just go a little bit off. So this helps, but it still has high sample complexity. You can just use a single model, as long as it's a really good model. If you have an excellent model, you can just use a single model and totally train in imagined space. And then there's this paper, which you don't have to have excellent models, but you train an ensemble of them and do meta-policy optimization. So it's kind of a new approach inside of this general class where you imagine data and train your policy on. Cool. And meta-learning, there's a whole paper on this. So this is used as a mammal, which seems to be one of the most promising approaches to meta-learning. Here's the update. So here you're doing an update to adapt to your specific task. And then here, since you want to maximize over theta, the original parameters, you're trying to make the original parameters so that after the update, your reward, because you're using the adaptive policy here, your reward is as high as possible on this task after one update. Cool. So why don't we also learn alpha, the learning rate? Well, yeah, you can actually meta-learn that as well. I just read the mammal paper. Cool. And here's some details on this. Again, you can go to the paper. It's quite interesting, and I'll probably do a screencast on this at some point. Cool. All right. So the meta-learning in this algorithm is just, so the different, meta-learning has different tasks, right, that you have to adapt between. So in this algorithm, the tasks all have the same space, the same action space. The only thing, same rewards. The only thing that's different is the state transitions, which is this learned model. These state transitions are different between the learned models, right? That's the only thing that's different between the tasks. Now, this is in contrast to what's been more typical in reinforcement learning, is that you change the reward. So you have your ant, and you can give it a reward for running forward, or you can give it a reward for running backwards, right? So you have the same environment there. The only thing you're changing is the rewards. And so that's been more common. So what we're doing here is just, kind kind of a new application of meta-learning to reinforcement learning. Cool. So, model-based policy optimization. Let's get into it. Here's the algorithm for reference here. Now you can see we're kind of learning the model here. So somehow we don't want, if all the models have the same error, then we aren't learning that, and that isn't so helpful, right? We want them to have errors in different places so that at each point we kind of get an idea of what the spread is of what the different models will predict. So we need to decorrelate the models so they aren't all the same. Now how would you decorrelate the models? Pause it. Well, initialize with different random weights, and they train them on different subsets of the data, right? And there's lots of other ways that you could vary this, but these are what they do. It keeps adding new data to train the models, so the models should get better over time. And as the models get better, you can train better policies on them, and then use those policies in the environment to collect more kind of on-policy data, and you use that to train the model again, and so on. Now, when you're training the model, that's just supervised learning, right? Input state and action, and an output state, right? So just supervised learning, so it uses standard approaches to that. I wanted to learn about weight normalization because I don't do that, but I do early stopping on the validation set, and yeah, normalizing inputs and outputs. Cool. And how do they do the meta policy optimization? Well, the different tasks, as we talked about earlier, everything's the same except for the state transitions defined by the different learned models. And then they do meta policy optimization here. So here's a question. What is this JK here? And how would we optimize it? So the JK is your measure of your performance. It's your loss, or here it's your gain, right? We want to maximize it. So here we're just going to sample using our meta policy. We're going to sample a batch, right? So a certain number of trajectories. We sample that, and then we do this update here. Theta denotes the meta policy. So theta k denotes the one-step adaptation using the kth learned model. Okay, so we get a batch using our meta policy. We do one step of adaptation. We get a phi prime. Now we want to see how well does this actually perform for this learned model. So here again, JK means that we're going to use the policy with parameters theta prime k, and JK means we're using the environment, which is where we're generating synthetic data with the kth learned model. Okay, so then we see how well does this adaptation work, and then what we want to maximize theta, which means we're going to update the original parameters to make this better. Cool. Yeah. Cool. So we estimate that, and then we update the original theta to make that better. Cool. So let's think of the big picture here. So we've got how we do our adaptation. We've talked about how we learn the model. So how ultimately does data collected from the real environment affect the policies that we're training? So how it affects it is what we collect from the real environment trains the different learned models, and then we do our meta policy learning on those different learned models. So it's ultimately through the meta learning on the trained models that that's how the real environment affects our policy. Cool. All right, and let's just look at the algorithm in detail, and we're done. So pause the video, have a look at this algorithm, and kind of